Good morning to everyone. The title of today's webinar is Enabling Trustworthy Health Data Processing through the Secured InnoHUB. Its duration is 3 hours, and the goal is to present the privacy-preserving techniques that are used by the Secured project and their applications in real use cases through the services and tools and libraries that the project will offer at the end. So the other thing we are trying to do in this webinar is to do a walkthrough through all these tools and services that will be offered through the Secured InnoHUB at the end of the project. Today's agenda is this. It is divided into two parts. In the first part, the introductory part, we are going to have a short introduction to the project by our project coordinator, Francesco Regazzoni, followed by a 25-minute tutorial on the techniques that we're using for people that are not familiar with the terms and the specific technologies, followed by a presentation of a demonstration of the Secured InnoHUB by Christos Avgerinos. Then we're going to have our first Q&A session and then a short break. Because this is a 3-hour webinar, we have 2 5-minute breaks, one after each hour. In the second hour, we will start presenting our use cases. We have 4 use cases. 3 of them are going to be presented during the second hour, followed by, whenever necessary, by a brief demonstration of the tools and services used in that specific use case that they are on the InnoHUB. And in the last hour, we have our last use case, followed by any tools and services that were not used in the use cases, but they are on the InnoHUB. Finally, we're going to have an open QA discussion session, and that's all. That will be all for today. At the end, you're going to receive, after the end of the webinar, you're going to receive a survey, a questionnaire that it will be very valuable for us if you complete it and submit it to get feedback from you and improve ourselves, but also to see if our services and tools have value for you. All right, that's all from me for now. So I shall give the floor to our project coordinator.
Okay, thanks. Can I share my screen?
Yes, of course.
Do you see my slides?
Yes.
Okay, welcome everybody to this webinar. I'm going to quickly introduce the Secured project, then I leave the floor to the other presentations. So what is Secured? Secured is the scaling up, secure processing, anonymization, and generation of health data for EU cross-border collaborative research and innovation. It's a project founded by European Union. And this is the abstract of the Secured project, the summary, and I'm not placing the abstract because we have to read it together, but because I wanted to. So the goal of the Secured project is showed in this slide, and it's here because I want to highlight what is exactly secure. So scale up, we want to improve scaling up a number of techniques, whatever scale up means, in the performance, also in the number of data that we can process, also in the number of entities that can participate, by increasing efficiency and improving security. Those are the 2 key aspects of the scale up: increasing efficiency and improving security in a number of applications related with health, addressing the current limitations that we have to deploy those technology in the health domain, being the lack of performance, being the lack of easy to be used tools for increasing the amount of data when you need extra data, for instance, by synthetically generated. How do we achieve this? We achieve this using algorithmic improvement, so modifying and improving the algorithms that are used to provide privacy-preserving techniques, or by improving the implementation, improving the efficiency in hardware and in software, or a combination of both. And we also try to have a generalization of the primitive to simplify the usage of those primitives, also for people that are not in-depth expert of the domain. What do we want to achieve by using those tools in the health domain is to have an generally increased quality of healthcare by allowing prevention, diagnosis, treatment, follow-up care, and in general well-being. That's not the only aspect. Whenever you develop a technology, you should also take care about the ethical and legal challenge related to that. So what we tried to do for the first time is to try to develop regulation guidelines together with the technology. Generally, our technologies are much more ahead than the guidelines. Here we try to have a development that goes hands in hands as much as possible. And all of those are demonstrated in 4 specific use cases related to the health domain. Real-time tumor classification and imaging for real-time tumor detection, telemonitoring for kids, scientific data generation, and access to genomic data. In Secured, we envision 2 main flows. On the top, the data flow, where the data are generated and processed, and at the bottom, the processing flow, where the computation is carrying out. And we want to make respectful of privacy and secure for the health domain in both the flows. Providing tools to generate the data where are needed scientifically, having tools to anonymize data where we use real the data, ensuring that there are no bias in the data, that the data is acting the anonymity that is needed. At the bottom, we have a number of processing flow that are already happening, and we try to rewrite them, try to make them respectful of the privacy and the security of the data by using and instantiating those processing using privacy preserving techniques such as MPC or homomorphic encryption on Federated Learning. The core of the project is the InnoHUB, where all the services and the tools will be made available. I'm not entering in much details on the InnoHUB because this is going to be a subject of a detailed presentation later on during the webinar. But what I want to show is only that we have a front end where everything is exposed and the back end that takes care of the bottom of the behind the scene part, such as formal verification that ensures that the data are going maintaining the properties that you want to have. You have a knowledge base where you can access services, tools, and other information and other tools to ensure that the privacy is maintained and the security is maintaining of your data. So with this, I would leave the floor to the rest of the webinar. Thanks for attending.
Thank you, Francesco. Okay, so now we move on to one Perez Baum from Atos Evident to start the presentation of the techniques we're using in the Secured project, starting with anonymization. The floor is yours.
Thank you, Gerasimus. Do you hear me?
Yes, we can hear you.
Okay.
I can hear you. I don't know if the others can hear you.
Okay.
We can hear you fine.
Yes.
Okay, great. Thank you.
Can everyone see the slides?
Yes, I can.
All right.
So I'm going to put in presentation mode. Do you see my screen now? Well, okay.
Yes.
Okay, thank you, Gerasimus. So hello, everyone. Good morning. My name is Juan Carlos Perez Baum, and I belong to the Identity Management and Privacy Unit in Evident, and I'm going to present the work made with my colleagues Miriam Villegas Jimenez and Dario Ruiz Lopez. So the question is why is needed to anonymize data? Basically, this is for preserving user privacy, which is the scope of private life that one has the right to protect from any intrusion. So be aware that more than 30% of the data comes from the healthcare domain. So due to the importance of this sensitive data, the access to this data is regulated by GDPR and European Health Data Space Regulation. So as personal and sensitive data has a high economic value, so then some threats arise affecting the rights and freedoms of the data subjects in relation to the protection of their personal data. So the illegal access could come from outside the organization. This is common, hacking and etc., you know, or generally, which is much more common from a member inside the organization. So this unauthorized access can be done, but also could be unauthorized access. In the last case, some additional processes on the data, such as destruction, loss, or alteration of the information can be occur, and this could be accidentally or unlawfully way. So we have to consider this aspect. So it's needed to use in this way some anonymization tool, which can provide benefits such as protecting and preserving privacy of personal and sensitive data like health information in order to avoid or mitigate as much as possible the user identification. Yeah, and in this way to accomplish with the different regulations, as I mentioned before, helping different stakeholders during the data sharing for improving the, for example, the treatments or the diagnosis or generate new medicines. So the idea in this way is to share, but keeping the user privacy and the data utility. But consider that anonymization is not perfect, and we have to keep the user privacy and the data utility. This will be the best, but we have this curve in order to find the best solution. So the final goal is to improve the patient's life and reduce the healthcare cost. So I would like to introduce some kind of concepts that sometimes can be misunderstood or can make confusion between them. So the first one, of course, is the anonymization. That is the conversion of personal data into data that cannot be used to identify an individual. This is an irreversible process because after processing, after anonymizing, we cannot obtain the original data. And the good thing for different stakeholders that share data is that the GDPR not consider this data as personal data. Other concept that can be introduced and sometimes is considered similar is the pseudonymization. That is to replace direct identifying information with a pseudonym. It can be a code, a number, or a hash. And we don't have additional information. If we don't have additional information, the person can be identified. So this process is reversible. For this reason, the table that stores the mapping with the identifying attribute and the pseudonym must be stored safely, for example, in a trusted security environment or in a safely way. So also important concept is the de-identification that implies to remove identifiers that directly identify a person, like a name, ID number, or the social security number. And this is a preliminary step of the anonymization. And some people consider that the identification is the anonymization, but this is not the case. It's the first step, okay? Also that other concept that we need to consider is the re-identification. That is the process to identify a person by using anonymous data and other available external data. This is the way that we say that anonymization is not perfect. And we have to consider the final purpose of the anonymized data and the progress in the technical aspects, such as the post-quantum computing that can facilitate the identification of the users. And finally, just to mention that the anonymization is part of the privacy-enhanced technologies that help to minimize the use of data, strengthen the data security, supporting the privacy by design, and preserving the data utility. And this can be achieved by using different tools or technologies that will be presented later on, such as the anonymization, pseudonymization, differential privacy, federated learning, secure multi-party computation, fully homomorphic encryption, synthetic data, and this can be used also in trusted executed environment. So the slide shows the data anonymization service main page, the graphic user interface, in order to anonymize the different data. This tool has been developed by Eviden, and this main page gives access to the different functionalities that are offered by the service that are included in the left side of the slide. And we can offer also an anonymization flow in order to use this tool, and can be used in different use cases, like this use case 2 and use case 3 that will be explained later on. Okay, and finally, these are some examples that of the functionalities that this DANS 2.0 tool can perform. On the left, we can see the preprocessing of the data set in order to calculate the age of the patient based on the birth date and death date. And this tool can calculate the age. And this new data set can be used for anonymize the data. And this is an example of the raw data set. An identifier, sex, and age can be anonymized based on age. And after the anonymization, we can see that the identifying attribute has been removed and the age has been generalized in order to hide the age of the patients in order to anonymize and avoid their identification of these users. And that's it from my side. Thank you all. And I give the floor to Balax that will introduce the Federated Learning. Okay, thank you.
Thank you, Juan Carlos. Balázs Peyó will now present the federated learning technique.
Yeah, hi everyone. Do you hear me and you also see what I'm sharing?
We can hear you and I can see what you're saying.
Excellent, thank you. Then I will get right to it. So my name is Balázs Peyó and I work at the Budapest University of Economy and Technology. And now I will give you like a federated learning in a nutshell overview, let's say. Okay, so I will explain what federated learning is. Essentially, it's a privacy-preserving technology, but it's not perfect because there are some attacks, like reconstruction attacks, which still possible. And if you want like another layer of privacy protection, then you can use secure aggregation on top of federated learning, which again eliminates some threats, but not all. And if you want to have like I don't know, a very good privacy protection, then you can use on top of this differential privacy also, but it has some trade-offs. And lastly, I will talk about contribution evaluation, because in every collaborative system, the incentives matter. So how important are different partners for the greater good? Okay. So let's dive into it. So in federated learning, there is a central server who has no data. It has a model, but because there is no data, this model is not a trained model yet. So what it can do is send this untrained model to different entities, for example, hospitals who have data, and then they can train this model on their local data. So they do just that, and then from this black model, let's say, they produce these blue and red models. And then this trained model will be sent back to the server. In this case, the privacy is preserved to some extent because the local data never leaves the hardware of the hospital, only the trained model is shared. And then this trained model is aggregated somehow, for example, averaging, and then the new model will be like the green one. But this was just one training round, and training is an iterative process, so then we repeat. So now we send back this new model, the hospitals train it further, and then they share it again with the central server until the model becomes sufficiently accurate. So you can see that this has like some built-in privacy protection because the data is not shared. And now I will explain why this is not enough. So what is training basically? So you have the previous model, you have your data, and then you compute the new model based on that. And what does the server see? The server sees the previous model and the new model. So basically it can reconstruct somehow to some extent the original data that it was used for training. So as you can see, even though the original data is not shared, in some scenarios, federated learning is insufficient because you can reconstruct the data. So because of that, usually secure aggregation is applied on top of federated learning. So what is that? So secure aggregation changes the federated learning pipeline in a way that it encrypts the local model updates. So instead of sending these blue and red models, only an encrypted version will be sent, so which will be meaningless for the server. But once aggregated these encrypted models, the final model is unaffected. So this is a beautiful piece of technology because it does not cost accuracy. So the final model is not modified, so you lose no accuracy while gaining some privacy. Because now the server essentially cannot do this differentiating attack. So it knows the black model, but doesn't see the blue model, so cannot see the difference and cannot infer what the training data might have been. Another thing to keep in mind though is that the server still sees the black model and the green model, so it can still infer, it might be able to infer in some scenarios what data was used for training. It just doesn't know where that data belongs to, whether it belongs to the blue or the red hospital, let's say. So while secure aggregation has another benefit from privacy point of view, it is not perfect. So we can apply differential privacy on top of that if we want to have an even stronger privacy guarantee. But differential privacy comes at the cost of accuracy loss or performance loss. So basically differential privacy is the golden standard in machine learning. So you can see it used everywhere, but the problem, so it works by adding noise into the system. And you can see here the trade-off. So the more noise you inject into the model's training, the more private the model will be, but also the less accurate it will be because the more noise you inject it. So there is this trade-off, and you need to do some computation, which is the optimal particular threshold for your use case. Okay, and finally, I just wanted to wrap up with contribution evaluation. So in any peer-to-peer systems, when people are collaborate, there are important incentives. What do I get back from participating to this collaboration, let's say? How important am I? And the thing is, this kind of computations, so computing this contribution, so-called contribution score, it's quite hard when there is privacy in place. So for example, secure aggregation hides the individual model updates. So it will be very difficult to actually say whether this is a good update or bad when it's encrypted, right? So this is like another clear trade-off between contribution evaluation and privacy, not just between privacy and accuracy. Okay, so this was just the background, and what happened in Secured is basically the following. So we build a federated learning system on top of Flower, which is an open source Python framework, a federated learning framework. And you can configure this through the Secured InnoHUB, and you can access it through the Secured knowledge base. So you will, I guess, hear more about these in detail later. And it was already mentioned that Secure had 4 use cases, and 2 of those use cases actually utilized federated learning. But again, you will hear more about these. So I just wanted to give you the background. So the secured federated learning supports secure aggregation by default, so you cannot even disable it. So that is the bare minimum of privacy protection. But if you want to have even stronger protection, you can enable differential privacy. Just keep in mind that will cost you accuracy. The final model won't be as good as you hoped for. And finally, there is also contribution evaluation included, which are compatible with these privacy preserving techniques. So even though because of secure aggregation, the individual update is hidden, still after the training, there will be like a value associated with each hospital, how good their data were or how important they were. And basically that's it what I wanted to share to wrap up basically the federated learning and the corresponding basics. So I will give the floor to the next speaker. Thank you.
Thank you very much, Balazs. So the next is Gareth Davis. He will present fully homomorphic encryption. Gareth, I am sharing the presentation, right?
Perfect. Yes, thanks very much.
Okay. I think you can see it now. Do you want me to put everything on the slide, or we're going to move through the slide? You're going to give me instructions.
Just move all the way through, and then I'll just describe it all in one go. Thank you.
Okay. Wait.
It has a very neat storyline, this one, but we can we can do the fast version of the story. Okay, so yeah, I'll just crack on and try and cover as much as I can. So yeah, thanks very much. So in this very brief presentation, I'm going to explain what fully homomorphic encryption is and how we're using it in the SECURED project. And I'm going to briefly touch on a more general concept, which is secure multi-party computation. So the most important word in the title of this, which is encryption. So encryption is something that you use every day. You're probably using it right now to connect to either Zoom if you're watching live or YouTube if you're watching later on. You'll be connecting via an encrypted connection. This is particularly useful, for example, when you're accessing your bank. And this means that someone who is observing your traffic and your data cannot see what you're actually sending. So they can't see your bank login, they can't see your balance on the screen, but they also can't crack this even if they store everything and try and break it later. So encryption is really a part of our daily life, and we use it all the time. But it has this feature where it completely scrambles the data. So we go from having something that's very nice and easy to use, which is data, which is your bank details, to something that's completely scrambled. And that means we can't actually use it for anything. So homomorphic encryption really allows the ability to do processing on data. So it's still scrambled. It's still scrambled in a way that someone who's observing the traffic can't work out what's actually there, but we can do processing. And the fully really means we can do any processing. So this is an extremely powerful tool. The idea was first conceived in the 1970s, but it was only worked out how to do this properly in 2009. And since then, there's been this very rapid development since everyone's realized how useful this technology is. So there's been a very large focus on machine learning inference. And we will see this later on in the use case 4, which is about cancer risk prediction using electronic health records and genomic data. And these are things we very much want to keep private. So these are the private data that we're going to do processing on, and that processing is going to be machine learning inference. So the diagram shows you exactly what happens. So we have some input, which we can send to some external entity, and then they can do some calculations on it. So this is, as I say, a very nice tool. The other place where this is used in the SECURED project is for keeping MRI data private in the first use case, which you'll hear about after the first break, so in about 30 minutes time. Okay, so this is homomorphic encryption. So a more general technique is multi-party computation. So homomorphic encryption is a special example of this. And as you saw in the previous presentation, secure aggregation in federated learning is also an example of multi-party computation. And what does it mean? So it's multiple parties. They get together to do a computation. So they want to securely compute on their individual data inputs while keeping those individual data inputs private. And this can be a bit hard to imagine, this generalization. So I'll give a simple example and then a more complicated example. So in a simple example, you can imagine a group of people who go to dinner and they want to agree that the person with the most money pays for the dinner. So they engage in a protocol where it comes out with, okay, the person has the most money. There is only one slide, by the way. The person with the most money is going to pay for the dinner, but they don't want to reveal the amount of money they have. So the way this works is they can use some very clever cryptography such that the inputs are hidden, which is the amount of money they have, but the outcome is the person who needs to pay and nothing else. So it really hides everything except the thing that's needed as the output. So this is a kind of simple example, and a more complicated example is how we're using the technologies in the SECURED project. So as I mentioned in our use case regarding health record data and genomic data, the entity doing the queries has an input, which is the electronic health record or the genomic data. We also have a service provider, which has a machine learning model. This is an input, which is private. They want to keep this machine learning model private. And the computation that they're doing is evaluating the machine learning model. So the output of the model needs to be sent back to the client. So as you can see in the diagram on the bottom left of the slide here, the querying client wants to get their output. They want to know the risk of the specific cancer that they're querying the model for, but they don't want either the input or the output to be revealed to the model owner. And that is exactly what MPC gives us in this case, instantiated by fully homomorphic encryption. That's all I wanted to do in this crash course. So thanks very much, and hand back for the next presentation.
Thank you very much, Gareth. So we move on to Alberto Gutierrez Torre, who will present the synthetic data generation. All right. Hello, Alberto.
Good morning, everyone. Okay, let's see. Okay. I'm Alberto, so we can go for the next slide already. Okay, what is synthetic data? So synthetic data is data that tries to mimic data that is already existing. So we want to produce new non-existing data using models trained to mimic existing data, it says here. So what we see in the left is that we have some real data, in this case mammographies. We do some modeling, some, let's say, learning, and with this we produce a model of our data. So then with this model, what we can do is to generate new data that initially it shouldn't be the one that we have given in the as a real data. So it's should be completely new data. So this is more or less in a very rough summary what synthetic data generation is. So we go to the next slide. Then what we do here in Secure is using diffusion models, which is a kind of deep learning technique. There are many other techniques, such as algorithmic techniques or, well, more neural network techniques. But in this case, what we are trying to do is to have this whole setup in which this highlight part, this denoising unit, is trying to map noise with real images. So what we do is we have the real images that we have, and then we try to map them to random noise. So that then, when we have this module ready, we can generate random noise to get new images. So that's in a nutshell what we do here in Secure for the mammogram generation, but we have more techniques aside of that one. Next slide, please. So in Secure, what we have is for image generation, we can generate mammograms, which is the one that we made, chest X-ray, which was made by Thales. Then there is an MRI interpolator for brain and breast imaging, which was done by ICCS. Then we have also time series, which in particular cardiotocography time series. So with the fetal heart rate and then the uterine contraction, which was made by BME. And then we are working on the tabular data generation now by integrating a library. And also something that has been left outside of the synthetic data generator because it's yet very experimental. This the histopathological image is built by BME. So all of this, except the histopathological image, is going to be provided by the secure service and tools. So next slide, please. So as you see here, we have mammograms, we have the interpolator, we have chest X-rays, then this cardiotocography that I mentioned before. So if you want to know more about this part, it's going to be presented in use case 3, which is the main use case for synthetic data generation. We also are working on use case 2 for the synthetic data, but the main core work is done there. And also, if you want to get a more in-depth view, we have the first webinar from this series, in which was devoted only for synthetic data generation. Next slide, please. So how is this provided? So we provide it as a library, so the code interface with Python, then a tool, which is the user interface for this library, and then also as a service. So, and then in the service, you have two options. You have InnoHUB, which will be presented later by our friend Christo. And then you can also use it with API calls. But with the InnoHUB, you will be seeing that it's really simple to generate data. Actually, this picture here is how, I mean, it's a bit small, but it's how it looks in the InnoHUB. We will see this later. Next slide, please. So, so maybe you are wondering what's the difference between service as a tool. So in fact, I would say that they are very similar code-wise, but the difference is where it's executed. So the service, this is executed in the cloud, particularly in this case in the InnoHUB. So if the application requires you to send data, you are going to send data to a cloud. So if this particular data is private, like medical data, you don't want this situation. Then for this kind of situation, you have the tools from the tool approach in which you deploy it locally in your premises so that you can send data to this application without sending it outside. So for example, the service approach can be used for the mammogram generation, the chest X-ray and so on, because they don't require input data. But on the other side, the tool, for example, the MRI interpolator, you require an MRI scan to interpolate partial slides. So in this case, what you would do is to use the tool approach. And I think that's it from my side. We will see now in InnoHUB if I'm not wrong, right?
Thank you, Roberto. Yes, we will move on to Christos Avierinos from Catalink, who is going to present InnoHUB.
Yeah, hi everyone.
Hello, Christos.
I'll just share my screen, okay?
Yes.
Okay. I don't know if the overlay is doing fun things. Can you see the InnoHUB working okay?
Yeah.
Okay. So right now registration is closed. So in order for someone to have access, you need to contact us, send us an email, and then we can sign you up with your credentials and your organization. So okay, I'll just sign in. Okay, this is InnoHUB, and this is a central collaboration hub for all the different experts that we engage. So that could be AI experts, that could be medical experts or researchers, and you can see that there are a lot of things going on. So we have the tools, which is a collection of downloadable standalone software. And again, some of those were already described. Some of those will be shown during the use case. I mean, by the use case partners. Then we have the services which are actual things or software that is running on the InnoHUB, and pretty much what Alberto showed previously. We have, for example, the synthetic data generator, where you can select the mammography, you can set it up, you can do whatever you want, and then you can generate some images, and after a while you get back with mammography image that looks something like that. There is a lot of things going on here. You can set some prompts. You can do a wide set of generation rules. There are other generators too, like, for example, the missing MRI slide reconstruction. There is the cardiotogram generator. There's a lot to just wander around and see how it's going. And then for other services, you have the anonymization user support, you have click and compliance, the risk assessment regarding the anonymization, and federated learning, which I'll go through in a minute. And then we have the libraries, which is it's a set of source code that has been deployed by the InnoHUB partners so that it can be included by other people in their projects, and it's the basis for things like what Gareth described previously, like the SMBC and the homomorphic encryption. It's for bias assessment. For example, the homomorphic encryption is used on the first use case that's going to be shown later on. And to use one of those, you just need to clone this, the official secured GitLab repository. You just need to clone that and use the code from that. So there's a difference between how you use these two things. So for tools, you have like it like Dockerized. So this is a standalone application that can be pulled from the Docker registry of the project, and then it can be run through Docker, and this would start the standalone application. Then I've talked about the service and the libraries, and then I'll go to the marketplace, which is a collection of data, models, and legal documents. Legal documents is a bit under construction right now, but we have data, so you can download. Here's some dummy data or some real ones that we have already been using for a while, and these can be downloaded. And you can also add a new data set here. I think you can see this pop-up here. Here you can add dataset name, the category, and access level, so it will be open, synthetic, restricted. And this is, this and the models that you're going to use are correlated to the use case that you're actually working. So here you can upload a new model, and here you can see some ready-made ones, and the data sets that have been already uploaded. So all these are connected for the services of the InnoHUB. I'll go a bit through the federated learning procedure because it's a bit, let's say, complicated, but we hope to make it easier for people to work with this. So the logic here is that once you have your user, then you can go to your profile and add your federated learring server. So you can see here that Catalink is the organization that I work for. So this is pre-populated here because I have signed up with this organization. So I can enter my IP here, which is never shown to anyone. Instead, what is shown is this Catalink dot, the name that I want here. So I can save the server's dummy server, and then if I go to services and federated learning, then you can see that I have some dumb experiments here. I can start a new experiment. I can give it, let's say, dummy name. I just hit random things now. And then I can just select some clients that are going to be included in my federated learning example. I'm just hitting random things now. And then I can select one of the two models that Balas talked about previously. And you can see that there are some things that I can turn off and on. So differential privacy, the noise I want to inject, is something that I can change, but secure aggregation is always enabled. And then there are some cross-validation things that I can check. And so if I hit next, I get the JSON configuration file, and there are some other things that I can tune here. And if I hit submit, then I see this new experiment number 5 here, which I can see the pending list of clients that I have sent a notification to. I can also send them a reminder. And then when I'm ready and when they have accepted my invitation, I can download, I can create this thing and then download the configuration, all the files that I need. So if I click this, I get a configuration file, I get the certificate that I'm going to need, I get, I think it's 2 more things, the .on file and everything that is going to be needed. And for all of these can be shown here on the tool page. So if I go to tools and then federated learning, I get a very, very detailed version and documentation of whatever's happening, what I want to do with my federated learning example. So yeah, this is pretty much. We have a link here to the SECURED project. As you can see, it's the InnoHUB requires a bit of exploration. There's a lot of things that we hope to be very, very useful for people of a wide variety of professions. So yeah, this is from my side, and I guess that will show InnoHUB a bit in the use cases too.
Thank you very much, Christo. From what I understand, since we're not going to the Q&A session, and do you have any question, by the way, because I don't see any questions in the chat? Any question about the privacy-preserving techniques or the InnoHUB? I will leave a minute or two for someone to type if anyone is typing. Christo, from what I understand for the InnoHUB, the services is something that someone that does not have a technical background can actually use more easily, like a doctor that knows the parameters that they need to set on its service. But it is, I believe, a little bit easier than the tools. That the tools need a little bit of technical knowledge.
Yeah,
Am
exactly.
I correct?
Yeah, from the technical point of view, the tools, I mean, the services, the tools, and the libraries are a bit technologically tiered, let's say. So the services is as much as you say, it's for people that have no prior, let's say, or a little prior experience of using such systems, but they do know what they're doing. So they're essentially doctors. They're medical. There are medical professions related to that. But then for tools, there is like a little bit of technological knowledge behind that. So if you know how to use the containerization machine that is Docker, then you can use them. There's standalone tools. And then if you're really, really fluent and you are, for example, a research engineer and you know how to import libraries on your code, then you can go directly into the libraries.
Okay, thank you very much. All right, since I don't see any comments, let's have any questions in the comments, in the chat. I believe we can do our first 5-minute break and let's be back at past 5 past, a little bit before 5 past 11. And sorry, 11. Yes. All right. Let's be back in 5 minutes. Thank you very much. See you in a while. Okay, we are back. We can now move on to our next speaker. It is Christos Stridis for our first use case 1. Good morning, Christo.
Hi, Erasmus. Hi, everybody.
Hello.
Can you hear me well?
Yes, excellent.
Right. You can see my share, right?
Yes.
Okay. Well. Okay. Okay. Hi, everybody. For those of you who know, seen the content before, this is the use case 1 of the SECURED project. Yeah. This is use case 1 for the SECURED project. It's related to the data privacy preservation in a neurosurgical environment in Erasmus Medical Center. Let me start by a little bit explaining in a couple of slides the problem. So we have a famous problem known as brain shift. I mean, there's tons of problems in the OR. But oh wait, maybe I should set it into present. You can see still see my screen, right?
Yes. Yes.
All right. Now you can probably see my laser pointer. Yes. Okay. So there's a famous problem in neurosurgery called brain shift problem. Basically, patients that have a tumor, when they unfortunately have to move to surgery, you cannot treat this by chemo or with by drugs. You have to do neurosurgery. The minute you open the skull to remove the tumor, there is a displacement of the brain, right? Because the brain is actually squeezed inside the skull cavity. And as a result, the MRI scans you have for the surgery are a little bit obsolete. They're becoming a little bit obsolete in the sense of displacement, as you can see in the screen. So pre-operatively, you see here, for example, this, I don't know why my computer is actually so slow, but anyway, you see the red contour as the original contour of the tumor, and in the MRI, the minute you open the skull, the tumor shifts, which is the orange contour. And the problem, of course, is that MRI is used as the navigational map for surgery in most operating rooms, right? These days, it's basically the defining all the stereotactic details for surgery. So if your base map is off, then all your surgery might be off, up to even a whole centimeter, which is too much, right, for displacing tumors. So we have a technology called ultrasound imaging. And the idea is that this technology is very highly portable. So it's not like an MRI. You can do it intraoperatively. So it's a very portable system that you can use when the skull is open. And as a result, you can get an updated image of the brain. So the idea here is, yeah, and you can see here also what happens if the tumor is removed, right? So even if you adjust for the initial shift, then removing parts of the tumor makes the rest of the tissue to cave in, right? So you have constant displacements the more you intervene basically in the brain matter. So the idea is to use a technology called ultrasound imaging, which is a portable system, a portable technology, and we use it in combination with MRI. And the benefit is, of course, that we can generate images like the ones you see here on the bottom right. So you can combine the DICOMs of MRI with the ultrasound images, and it gives us very good insights both on vasculature, right, structural images, but also functional brain dynamics. And that's very useful because different parts of the brain are collaborating, let's say, dynamically to perform tasks, right? So when you see a patient asleep, during surgery, you might think it's part of the brain that is affected by the tumor is not doing anything super critical. The minute you wake up the patient, you see, for example, that for a certain verbal task, you ask him to repeat something, suddenly that part of the brain is activated. So cutting the wrong part of the brain out might, for example, impede speech. And so this is used regardless, but we're using this technology for also correcting for the brain shift. The downside of the technology is that because it's so high rate and so high detail, it generates north of 6 gigabytes per second of data, and that's for 2D images. For 3D images, is a multiple of that. The solution we have in security is as follows. So this is the current setup we have, right? So we have the neuro OR on the left, and we have the radiology department on the right. And if you notice on the at the bottom left part of the image of the drawing, we have the so-called PDI data. This is powered Doppler images. It's what I just showed you in the previous slide. So this nice orange hue, artificially colored images is basically powered Doppler images of ultrasound. It's process ultrasound. So this kind of information is being generated on the fly during the OR, while the MRI data is routinely collected the day or a few days before the surgery, ideally as close to the day of the surgery as possible. And so the radiology department is responsible for collecting this data and then transmitting it to the surgery room, to the operating room on the day of the surgery. And so the new modality is ultrasound. So the idea is that you want to combine the ultrasound data you can see on the left part of the picture with the MRI data and do a so-called code registration and generate the images such as the ones I showed you here on the previous slide, right? This is how the thing works right now. What we want to do to correct for brain shift is add an extra couple of boxes in the diagram, what you can see on the bottom of the drawing. So we want ultrasound data plus a little bit of extra data, so tracking data, which is basically anchor points and some region of interest for the MRI, because otherwise you need to do it for the whole brain. Anyway, these are details on the bottom. It doesn't matter, but we need basically, by and large, we need PDI data coming to a box, a processing box, let's say computer inside the OR that does PDI interpolation. So it's basically uses the PDI data to adjust the XY coordinates, if you will, XYZ coordinates of MRI. So we're using the coordinate system of the PDI to adjust the coordinate system of the MRI image, right? And we call it MRI regridding, right? And once this is done, then we need to send the updated MRI DICOM slide deck, if you will, back to the computer that does the code registration. So instead of using the original ultrasound data that you can see on the top, it uses the regridded MRI data and the ultrasound data to do the code registration. You will notice that there is also this fMRI in parentheses, because in principle we can have extra processing on the MRI data done. So there's extra layers of data processing we can do on this base set of MRI data. Okay, so this is the let's say technically the way to correct for the brain shift. However, the problem lies in the fact that the MRI data, the processing we need to do here, this PDI interpolation and regridding part of the MRI is generally a very expensive process, right, computationally. And we cannot afford to do it inside the the operating room, because of limitations of space and of also even heat dissipation and noise, right? You bring a big computing node with big fans, right, to keep the system running at high throughput, then it disrupts surgery. So, and it looks something like this, right? That's the reality of an operating room. It's very organized, but there is a lot of things going on. So the last thing you need is bringing a mini, like a server node to do crunching there. Okay, so what the solution is, I just spoke about that. We have different concerns. The solution is to send it to the cloud and back. And there's a technique called, and of course the question is, do I trust the cloud that I send it, right? So the configuration that we want to do is essentially this. So we have the OR, we send the plain text ultrasound images, right, to the cluster. I also have the radiology department sending the MRI data to the cluster. Now, the cluster could be trusted or untrusted. In the general case, we assume that it's untrusted. So the MRI data needs to be sent encrypted. In the general case, also the ultrasound needs to be sent encrypted, but there is currently no known way of associating brain vasculature uniquely to the patients, right? So we don't need to. We could, in principle, send also this encrypted, but the key problem is the MRI. If you send a proper set of MRI data, you can also see the face of the patient, as you know, right? Because you scan the whole head. So you send the ultrasound data with the encrypted MRI data. You need to do here the reading and send the data back to the operating room where you decrypt the MRI and you see the images. Of course, the question is, how do you combine, how do you do this regrading process with encrypted MRI data without tipping your hand? And so there is a known strategy that is called homomorphic encryption, right? And the idea is what we just showed in the previous picture. So I have the data, I own this data, I can access this data locally, but for a number of reasons, I cannot process it locally. So I offload this to a third-party provider. And the way to treat the data in a data preserving, privacy preserving way is do homomorphic. One of the ways is to do homomorphic encryption. And that's what we did in this case. So revisiting the previous drawing that I showed you, this is how now this is modified. So I introduced an extra layer, a sandwich layer between the neuro OR and the radiology department. So I prepare again my PDI data on the bottom part. I am prepared to do co-registration on the top left, but what I do in the meantime is I introduce this extra layer in between. So I have this HPC cluster, which is generally untrusted. Could be inside the premises of the general, medical center here, or could be outside, could be a third-party provider. For example, here we have a corporate contract with Microsoft's Azure cloud services, and they're using it heavily, right? Right. And so what you do is you send to that cluster the data as before, like plain text ultrasound, but remember this is called powered Doppler, so PDI, plus some extra small details here on the bottom, the blue lines. The MRI is now is first encrypted and then sent to the cluster. And so here in the middle, in step 4, you do the homomorphic evaluation between the PDI data and the MRI, and you do the so-called regrading process, right? The regraded and still encrypted MRI stack is then pushed out of the cluster, back into the OR, and then in step 5, you need to do a decryption, but decryption is not that much of a deal. We can do it inside the OR. And then regrading, co-registration between the PDI and the updated MRI ensues in step 6, right? And the net result is what you see here. That's the outcomes of the project. So we have the original MRI data slice on the top left. We have the brain shifted version on the top right. This is, of course, a demonstration example. If you do the delta, if you subtract one from the other image, what you see now is basically the brain shift on the bottom right, on the bottom left. And if you do the correction via what I just showed you, the homomorphic encryption with ultrasound, then basically the difference between the corrected image and the original image is basically a net 0. There is some small artifacts at the bottom, as you can see, some yellow line here on the bottom. This is basically because of the interpolation. So basically, the image is a little bit tilted up or down, so there's some edge artifacts because of processing, basically. But you can see that we restore the original placement, or we track basically the shift of MRI. That's it. So this technology, this library, it lies. You can find it in this link that I have here. I believe that the homomorphic encryption library was presented just before the break in my presentation, in the previous slot, right? And you can get access to exactly that library. There is also a test bench that you can, if needed, that you can deploy this with 2 container modules, emulating 2 computers. So you can take this 2 container setup and replicate what I just showed you, right? From location A, offloading to location B for a greeting, and then back to location A, right? So you can find this all on the InnoHUB repo. thank you very much for this. The people who did all the work are shown here. So this is the Erasmus team on the top. So Peter Krausinga, Stefanos Florescu, Arber, Demi, the technicians, and Leonard Landsmeer helped a lot. And on the bottom, of course, the rest of the partners in Secure project that they helped a lot, predominantly University of Amsterdam and ISI Athena. Thank you very much for your patience.
Thank you very much, Christo.
Yeah.
Are there any questions about use case 1 and homomorphic encryption, since this is the subject? Let me check the chat. If anyone is writing something, please raise your hand so to wait for you. Okay, we don't have a question, so we move on to the next use case. Adrián Muñoz is going to present use case 2. Hello, Adrián. Good morning.
Hi, Gerasimos. Okay, I will share my screen. You can see it, right?
Yes, yes.
Okay, so hi everyone, my name is Adrián, and we at the intensive care unit of the Infants Hospital Niño Jesús work with children to try and give them the best care possible. For accomplishing this mission, we try to leverage data. At Hospital Niño Jesús has installed what is known as a high-density clinical information system that, contrary to traditional methods of manual register or conventional clinical information systems that have multiple drawbacks and few advantages, a high-density clinical information system stores data of each patient for every vital sign that is tracked every 5 seconds. So that's a lot of data with high frequency. This makes this system a very powerful tool for developing and testing AI functionalities and applications. Right now, we are here on the red rectangle, where we have powerful research tools that are useful for development of personalized medicine, but with the drawback of the having to implement new technologies. So because all of this data wouldn't be valuable if we don't not use it in a safe and privacy-preserving way, these are our partners here at the Secure project that come into play and help us with it. We have collaborated especially in the development of anonymization techniques and a specific tool for us to use with the private company Atos Eviden, okay? And also with the development of a Federated Learning setup that will allow to share results and model with other hospitals that are like us without sharing specific data. This was done in collaboration with the Laboratory of Cryptography and System Security of the Budapest University of Technology and Economics. So, okay. So here we can see a simple example of the pipeline regarding the integration with the DANS, that is the Data Anonymization Service, inside the use case 2. So where we have here inside our use case a collection of time series that our system at the hospital generates, and then we apply the anonymization, and after that do also an anonymization assessment to finally build a data lake for our time series that we can then exploit. If we see it in a more detailed way, the dance service, we can see that it involves different tasks like selecting a data set, then loading that file with metadata. It allows us then to identify different attributes, hierarchies, set which parameters we want to anonymize and which we don't. And then get some statistics to see if the results of the anonymization were successful or not, and to keep going to the next steps. Speaking about the architecture design of the service, it consists of a modular design based on microservices with a visualization layer that is a graphic user interface, also an API to call functionalities directly and to integrate, an orchestrator that chooses which one of the anonymization's implementations to use depending on the specific problem that we are trying to tackle, and also a persistent layer to keep it consistent, and support service like preprocessing, merging files, utility functions. Here are some of the features that it implements, this data anonymization service, but I will mention specifically the ability to have both a graphical interface and also an API that can be called and integrate into other tools or workflows that we might have or might develop. This is something important for us because being in a real-world setting, where we have clinician and also staff that is more technical, it allows us to choose between which implementation to use for each investigation or task. So maybe clinicians are more familiar or easy to work with a graphic user interface, but at the same time, if we can integrate and connect in a workflow the API calls directly, it makes it easier, less repetitive. It's most suitable for real-world scenario. Here you can have a look a little bit of the data anonymization service user interface. It is straightforward. We can select the data set that we want to anonymize, then give some metadata information that will help us to do the task, and then choose which are the parameters that we want to configure in a certain way that we get the utility and also the privacy that is good enough for the specific task or mission that we're doing. Okay, I wanted also to share a little bit of an example of what exactly we are doing or how they are helping us. So in this example, it is normal for us to have a table with the patient's data. For the record, this is just synthetic data. It's not actually the information from the patients. It was generated to be, so to explain it, so an example. But yeah, we usually have the fecha nacimiento that translates to date of birth, and that it can be some identifying information from the patient. So what we do is to do an age calculation, and instead of having the date of birth, have the age in months. So it obfuscates a little bit, but it still has that clinical value. Other examples, it is when reading the records measurements, okay, of the different time series with its value and timestamp. You can see in this table that we have a column that is called fecha, that means date in Spanish. So what we can do is to randomize that that date, but still keeping it consistent. So one data point remains after the one that follows. So the signal doesn't get altered, right? Here you can see the problem with a slight different solution also, that is to transform the date into a serialized version. So data point number 1, data point number 2, and so on. But still we can see that we reconstruct the signal still is a valid values, and the data is still consistent as it is. After speaking with clinicians, what we learn is that they value the most, so they value to obfuscate the date, but they still want to maintain the hour of the day, because the time of the day can be clinically valuable if it is noon, afternoon, or midnight. So that is something that is important for them. But having the ability to be able, depending on the investigation, to configure and do it one way or another, that is also useful for us. So that's a great thing that our partners keep it that way. Okay, so as I mentioned earlier, other of the secure technologies that I want to highlight is the Federated Learning setup that we are working on. I won't go into detail on how Federated Learning works, because already there are other partners that will explain it better than me. But I will highlight why it's very useful for us, and that is because we have this high-density data repository. But that doesn't mean that we have unlimited number of patients, right? So if we have that framework that allows us to collaborate with other hospitals, public databases that are available, and even data that has been generated in a synthetic way, that makes that exploitation of the data much more useful, but still preserving the privacy and self-governance of each one of the entities. So yeah, just having different sources for our models, for our algorithms, makes it much more useful than just having our own one, right? So, and what do we do with that, all of the data that we manage to gather from different sources or own? Well, some of the real world applications that we have been working after asking medical staff are the anomaly detections, the change point and even predictions, and also the help or support that large language models can give in day-to-day medical activity. So I will now introduce a little bit of the use case particular applications. First one is the anomaly detection, where we have seen that there is a problem in general for the nurses that are caring for the patients, is to help to differentiate real medical emergencies from just anomalies that trigger false alarms. Okay, and here the objective is to develop a service that is capable of detecting anomalies in physiological parameters like heart rate, respiratory rate, and different ones, the ones that we measure. Then this way we can develop an intelligent system that reduces disruptions for medical staff caring during their normal day shifts, and they can provide the best care when it matters the most. Here we can see, so we experimented with different methods. Here we can see one of the methods that is, sometimes we have a parameter, a vital sign that is measured in two different ways. For example, here the heart rate that is measured via electrocardiogram and also via pulse. And then by comparing the signals, we can see that here and here, there were like anomaly data. So that is probably an anomaly. We can show it to the medical staff, and then do not disturb them in, like, do this automatically, and it doesn't trigger the alarm. That's one of the applications that we have seen. Pretty straightforward, but it is useful for them. The second one that I wanted to talk about is the change point detection. So here you can see these are real images of the setup in the intensive care unit of our hospital. And the problem here is that at any given time, we have multiple patients, but not all of the patients have the same level of severity. Maybe some of them are stable, some of them are really critical, and the staff knows it, or maybe they are critical and the staff doesn't know it yet, right? So how can we try to focus the attention when it matters? No? The objective here will be to follow the evolution and trends of age of the patient and focus on the specific moment when an event is happening, and that patient needs the more attention. For that, what we have done is to develop a model of cluster classification that it works that when a significant variation on the underlying data occurs, we can label it as a different cluster and detect the significant changes that has been produced and focus on the attention of the clinician on the specific patient in that moment. So here, for example, we have the different signals and 3 moments that we can see, you know, an initial moment, then a second phase, and a third phase. Since we don't have labeled data, we cannot say what is happening. That is also another thing that we are working on. And also, this project has allowed us to start labeling data, but so far we do not have that. So what we can tell is that here the distribution was in some way, then it changed, and then it changed again. So what we are going to say is, in this moment that the distribution changed from one to another, here something is happening. So maybe you, the clinician, should go and see, is everything okay? And with the expert eye, check if you can do something for the patient. Okay. And the last one application that I want to talk is regarding large language models. Here we see 2 problems, and is that usually medical staff need to write reports, and sometimes those reports don't get filled in the quality they have to. Also, with the appearance of third-party tools of language models, it is very tempting for medical staff to use them, but they are maybe breaking some terms and conditions from the hospital or from the government. I mean, at different levels of different levels of bureaucracy. So the objective was to develop a self-hosted and privacy-preserving model that will allow medical staff to use it, but still keeping their, without sharing, right? Without sharing with third parties. So here we can see an example of analysis that will one of these models do. And well, we can see that it says that based on the provided vital signs, clinical interpretations will be this and that. Okay, so the goal here is for having some basic template that then the clinician can edit and go on and be much faster without having this temptation of using another tool that is out of the scope of this secure infrastructure that we have built, right? So yeah, that's a little bit everything I wanted to talk today. We will be very happy if you want to further discuss and you are seeing this and you want to contact us, please do so. If you are working in something related, please contact us at, well, my use case to leader, Andrés Castillo Sanz, at the Hospital Infantil Daniel Jesus. That's everything. Thank you very much.
Thank you very much, Adrian. Okay, so now the anonymizing tool is going to be presented after use case 3 on the InnoHUB, because it is also used in use case 3. But now Hamza Agelal is going to present to us the service that can be used, that is used together with the anonymizing tool, which is the anonymization decision support service. Sorry, did I say that correctly, Hamza, or I said the wrong?
It's actually the de-anonymization risk assessment service.
Risk assessment, yes, you're right.
Yes.
The anonymization risk assessment, I always confuse these two, as you know. Okay, so the floor is yours, Hamza.
Yeah, thank you very much. For myself, it will be a brief introduction. I'll just share my screen, share the InnoHUB access. Okay, so I presume it's visible.
Yes.
So basically, I'll briefly introduce the de-anonymization risk assessment service. So as the name says, it's de-anonymization risk assessment. So basically what we planned in the service, and we developed a service that will provide a kind of estimate on the de-anonymization attack risk on specific data types. We focus on ECG signals, AHR records, and genomic informations, since they contain sensitive information, nearly unique or identifying information that could lead to de-anonymization attacks. So basically, our service is providing like a simple guided way to have an overview about de-anonymization risk based on informations that a health professional or any user in a simplified way to have an idea about the risk related to the data that was input. So either metadata or a sample file that can be uploaded. So basically what the service does is, let me just go down. It's basically what you need to do is to choose the data type that you want to estimate and assess the overall de-anonymization risk on. And then once you choose one of the three options that you have, either ECG, electronic health records, or genomic data. So basically you can upload and describe the data set that you have with multiple information that you can actually choose. And also we provide the option to upload a sample data that you can upload to the service. And on the back, what we do is the system is evaluating dependent on the components and contents of the file, or also the form that you filled, to do taking into consideration the studies that we did on the real de-anonymization attacks and existing research and proven attacks, to provide and checks for the risk on linkage attack, inference attack, prediction, and membership. So basically for the upload of the file, we're requesting to upload a sample file for compliance purposes. So the users are not supposed to upload their original data. So either synthetic data or a similar one that's not containing personal information. So behind this interface, we rely on the research basically from the literature and techniques and the file-based metrics that we take, and also all the quasi-identifiers that we have, or the rare variants for each type. For example, here we have ECG, or if you go to genomic, so genomic related data that could affect or kind of play with the de-anonymization risk. So basically it's a simple service, easy to use. You choose the data type, as I said, you fill in the form dependent on the information that you have or what you want to get an idea about, or the components of your data set. And you also have the possibility to upload a sample file. And what is done is a few calculations are done in the background, calculating entropy, seeing the columns and uniqueness on the data set, including also the file assessment that is done. Basically provides the analysis output, which is a risk summary per attack and the chart visualization. And also what we provide is a detailed explanation and recommendation based on whatever was input to help if you need to change things on the level of your data. And also we give in best practices by the use of anonymization methods, basically, and also graphs showing estimate of risk for each attack type that I mentioned earlier. So I think that's it for our service. So I'm here for any questions. And sorry, forgot to mention that I'm a PhD researcher in University College Cork. So for any inquiries, don't hesitate to contact us. To provide more details about the servers.
Thank you very much, Hamza. Are there any questions for Hamza or Adrian from our participants? In case you want to contact any of the speakers that are presenting today, in our website there is a web page for this webinar where you can find all the speakers' information, and if you click on the image in the profile pic, it leads to their profile, to their online professional profile where you can contact them. Okay. If we don't have any questions, we can move on with use case 3. Peter, are you ready to use? Okay.
Yes. Can you hear me?
Yes, yes.
So I share my screen.
All right.
Can you see my screen?
Yes, yes, we can see.
Okay. So, hi everyone, I'm Peter Parner from the Semmelweis University Budapest. I'm presenting now the use case 3, which demonstrates the application of synthetic data generation in an educational setting. So this is a usual educational scenario where we are the students are looking for the start of the course. I just wanted to say a few words about synthetic data generations. So it is usual that, for example, a face image is a personal data. So everyone wants to hide somehow its identity, where for registering to any websites or other cases. Here you see an example of a generated image from the image on the left from my colleague. And you see that by generating several alternative images, one can really change its identity. That means it will hide some personal information. So yeah, this is what I see, that what I told you, that especially in social media, but in general internet usage, it is a very common solution for protecting personal data. In healthcare setting, this is a especially enhanced problem, because healthcare status of individuals are highly sensitive. So, but in such an environment where one has to be very careful with data sets, or that means images or any tabular data or any other clinical data, one wants to teach the new generation of doctors, but they but when they do not see real cases or such cases where the anatomy or the disease characteristics are clearly shown, if they do not see such data and they cannot practice with several variances of such data, they cannot be prepared for their future medical life. So therefore we are focusing to application cases in an educational setting. The first one is a homework training, where students want to see lots of different data, lots of different images, and those images should be specific for a given disease or for a given problem. The other scenario, which is very important, the exam cases, where the students should report what they have learned and what they are knowing after the course. In such situations, the exam cases has to be unknown for a student, and they should be always, or in either case, they should be always different for each student and for each exam. Otherwise, the students will can learn some specific non-disease related characteristics, or just memorizing the serial number of the exam cases, and they could pass the exam without real knowledge. So this is why the students need lots of examples, and the lecturers need reliable, but if required, reproducible samples for exam cases. Here, as Alberto has already mentioned in the introduction, theoretical background, we have several types of data sets that are helpful or important in medical education. One example is a time series data set. There are 3 image examples, and the last one is a tabular data example. This is the time series example, where you see that this is a real recorded data set which monitors a baby and their heart rate and uterine contractions, and from such data sets, the doctor has to be able to read out if the baby has some problems and they should give an earlier birth or some other interventions are required. It was already mentioned and will be also more, shown in more details by Alberto that how these data are generated. This is also a slide from Alberto. So the main setting is that from real examples, model was trained, and this model can generate an image. And this scenario, the model in this educational scenario, the model runs on the InnoHUB server, and the generated image will arrive on the student computer via a HTML GET request, and this GET request contains some parameters which specifies what type of image and what the details of the image should be generated. So this is the latent diffusion process, which is used both for the mammography image generators and also for the chest X-ray example generators as well. In the chest X-ray example, it is also solved that when the so-called biased dataset problem is also handled, that means that it can occur easily that the real training data set is unbalanced. That means that, for example, more males are represented in the image data set than women. So, but in real application cases, the patients are usually approximately at the same number from the both genders. So the practice and the educational examples should be also balanced, and that was solved by the Thales team. Besides the basic generator problem, they also solved the unbiasing problem. I just want to shortly mention the MRI example, that means that generates a missing slide from a series of slices in a MRI image, and the user has to guess whether the generated image fits into the series or not. And the last example is the data set, tabular data generation. The tabular data generator is actually a clinical data generator where several population-related data set or characteristic data are generated, or other numerical or categorical data that can describe a patient. And such data generators are very important because those clinical data are highly sensitive. So if statistical courses are taught to the students and they want to explore a large number of cases or large number of the patient data, or huge data sets of patient data, it is the best practice if a generated data set is given to the user, to the students, where all the individual data are not related to a real person, but the statistical features are very close to a real setting. So we have implemented the use cases in our educational software framework, the module system. Here, if you want to play with this sample course, you can use the QR code or click or copy and paste this URL, and I go to this website. I have already logged in order to avoid any delay. So I just wanted to mention that if you log in, if you go to the login page, you can give any username that you prefer. You should not use your identity or email address, real email addresses. So this is our online course. That it gives it is focused on the cardiotocography generated data, because we wanted to show how online course can be looked at. So here there are several details of the medical content, where a medical student can learn what are the main features of such a data set. So here you see some IDs, and there are more details as well. So, but I want to go further to data generators. So when the basics are known for the student, then it is time to see lots of examples where they can learn how such a data set can look like. And here comes the data generator in play. We have constructed or created some examples. For example, one can generate different cardiotopographic data sets based on the sex of the fetus. And if I click several times on different on the categories, the generator creates new data sets or new time series that are typical for that chosen gender. This can be done for the pregnancy status or delivery status as well. The page looks quite similar. Here I wanted to show you an example which presents a big example for the medical students that they should get some basic ideas how the anonymization works. The most important, so one of the important steps in anonymization techniques is the adding of a noise to a real data set. So here, using this slider, a student can play and see how this noise destroys the information in the data set, and which makes a data anonymous. Now I turn to the synthetic mammogram generators. They are the images. Here I show you that there are three exercises. The first one is a homework example where a student can select typical parameters for a mammogram. This guidance scale is just a generator specific parameter, and then it can select, but then it can generate an image, and again it can generate new images and look at them, how they look like and how informative these images are. I want to show you the example cases. The difference between the homework and the exam cases are that in exam scenario, the images should be pre-generated because an exam should be evaluated several days later as well, when there are questions or problems from the student side. So, but these images are generated and that ensures the high variability between the students and the exam and the year's exam years. Now, here's a typical image, and the student can choose what the image is showing. I want to focus on the image generation aspects of these images. As you see, one can see the main characteristic patterns of a mammogram, but it shows some errors as well, because there is a shadowing effect on the image. So if one uses a longer generator setting, where the generator itself iterates quite longer on the image, that means that the image generator, as it was already mentioned by Alberto, and it will be also shown, that it is a iterative process. When this iteration goes longer, then the image will get a better quality. Here you see a real good quality image, but it takes really long time. And I want to show that in an exam setting and other homework setting as well, it is important that the lecturer should overview and check the images. This is a typical failed image generation, where actually some local patterns are shown, but the general mammogram characteristic, the mammal, is not quite visible, and this is a really bad example for such a generation. So one has to be careful, and it is an active research question how one can check and construct an error function that can automatically recognize such failed images that are similar to real mammograms in all small details, but the whole image is not well enhanced or contains several errors. The time is running now out, so I just want to mention
Peter,
that
the time has run out.
Similar images for chest X-rays, and there are also some similar scenarios for the MRI and tabular datasets. So that was.
I will mention very briefly that before you go to the video, that all these tools about synthetic data generation are also presented in our first webinar. So someone that needs or wants to go into more detail, they can go there on our YouTube channel and see the first webinar where all these techniques are explained in detail. Do you have, Peter, also a video from the anonymizing tool?
No, it was uploaded to the presentation folder.
In this demonstration, we will first replace the dates of a file with a column with edges using the pre-anonymization tool, and next we will proceed to anonymize the resulting file with advance. So, I go to Process-Based Attributes, I select the file to anonymize. Upon selecting the file, you can see the content of the file, which it's start and final columns, which are birth date and death date. And I can see from here which is the timestamp format that I need to select, which is the one that starts with year and with -6, this one. Now I select the unit that I want the calculated age to be expressed in, a name for the column, and a name for the exporting file. So I calculate the interval and export. Here I have the resulting file, which you can see that already contains the calculated dates. Next. Normally, in the next step, we will remove the previous date columns from the dataset. But in this demo, we will skip this step because we are short of time, and instead we will simply use a previously saved file where we have already done so. So I select this file that we have already prepared. Here it is. Now I proceed to fill the information of this file, some name for the new data set, some keywords. I select the type of data set, its format, the size, the delimiter of the data set, which is the semicolon in this case, and the most important thing, the type of tool that we are using for the anonymization, in this case, amnesia. So I save the information and upload the file. Upon uploading the file, I proceed to set the attributes, definition of the attributes. So first identify that the identifier is the PID, it is an identifying column. Sex, it is a quasi-identifying, and X is a quasi-identifying column. Next, I select the types of the attributes, which is ints. And next, I will assign the hierarchies. In the case of LDANS, we don't need to assign a hierarchy for the identifier because it will automatically fill all these fields with a mask of an asterisk. So I select the hierarchy files that we have already prepared in advance for the two columns. And next, I proceed to update the attributes. Now we are ready to execute the privacy model. In this case, we will using, because we are short of time, a key anonymity model. Here, with a value of k of 4 to guarantee at least 4 different values per each row. So I validate the parameters, I save them, and I anonymize the file. After anonymizing the file, I can download it here, and I can also download the statistics here. Here are the statistics, and we have also downloaded the anonymized file. Here it is. Here you can see that we have the resulting file with the new columnates that has already been grouped to anonymize it. And this is all.
Juan, do you also want to present how we actually find this tool on the InnoHUB?
Yeah, of course. I'm going
And
to
then we'll go to
share my
Alberto,
screen
since-
again. Yeah. Okay.
since
I
you already
will go
presented.
very quickly. I'm going very quickly. This is the previous presentation. Yeah. For finding this tool, you have to first to authenticate into the InnoHUB. I'm authenticating through the as a guest user. You have to go to the tools, okay, and go to anonymizing. Exactly. Okay, in here you have different information related to this, and you can find information about this. We have to update this because this is not completely adequate and correct, but the idea is to go update the information with the data and information we have included in the GitLab of the project. So we can go to the GitLab to the project. And in here, we have the different information we need for managing this tool and for deployment and accessing this tool. This is information related with the API that we offer with the service, and these are the instructions for the deployment of the tool. First of all, we have to configure some configuration files in order to adapt the situation in the premises where the tool will be deployed. As mentioned in some of the presentations, this tool has been need to be or should be deployed in the premises of the data provider. We can, of course, install and deploy in a third party, but we have to trust in there. But this third party or cloud, maybe they are honest, but probably they are curious and they can access our data and learn from our data. So the idea is to deploy this tool in the premises of the hospital, research center, or whatever the data provider is placing the data sets. So for the installation and execution, we have to log in the registry of known as the knowledge base. And once you have registry in there, you have to deploy these Docker images and run using the Docker Compose we included here. Okay, this is the Docker Compose, and updating this Docker Compose with the configuration parts, you can run this tool. In any case, we have to update all of this information in the InnoHUB in order to the user can get access to this, because I understand that this the GitLab repository is only for the secure partners. Okay, and that's it. I don't want to spend more time in this.
Thank you very much. Thank you very much, Juan. Okay, now, Alberto, will you also present an example of the synthetic data generation service?
Yes, can you see my screen?
Yes.
Yeah. So we go directly to the service. So the tool, you can find it here. It's similar to the installation that Juan mentioned, all is described here. So we go here in services, then we go again, as Christos mentioned, in synthetic data generator. And then here, as he's shown, we have these different generators, right? For example, we have the mammogram one that Peter showed. So in here, we have all the parameters that the mammogram generator offers. For example, this one is interesting because you can check the information that you are putting here in the image. And it's as simple as you click here on generate, and then you wait for the generation to be over. But meanwhile, well, it's done already. As you see here, as Peter mentioned before, we see that there are some colors here and there, so the image needs refining. So there is this parameter which is called inference step, which is this iteration that Peter mentioned. So if we get it, for example, to, I don't know, 60, the generation is going to take a bit longer, but what we'll see here is hopefully better. So, for example, these parameters here are the which breast it is, which projection is this, how big it is. And what we see here is now the image is quite better. So we have this kind of shadowing here, but the quality is far better now. Then if, for example, we want to download this image, we can click on here and download set, and you will get a zip file from it. But now let's show something completely different. For example, CTG generator. So in here we have this steps generate the steps parameter again, which is the same thing as the previous one, and then the guidance scale, which is something that is already present in the mammogram, which means how much the generator has to follow the original instructions. So this is too much, I mean, in 20, and too few in 0. So let's get the samplers. They are the processes that generate the data in the end. So let's get this one that is the slow but is the best quality. And we click here on generate. It's going to take some time. But in the meantime, what we are doing here is to generate this, as Peter showed, the uterine contraction and the fetal heart rate of the baby. And later what we are going to get here is a button that says download everything. So download set. So we have generated these 2 time series. But the cool thing here is that this is not just an image, but it's also, so this is the original SVG image. This is the PNG that we are showing here. And this is the actual data. So if we open it, we will get the time series here. So time 0 is this one, C1, and so on. So you get both the image and the original data. And this is more or less the same for the chest X-ray. This is another type of generation for CTGs. And this is the, I hope I have it here. I think, yes. So this is the MRI interpolator in which we say, okay, the sample 2 of the time series, or the slices of the MRI is missing. So actually, this should be opening. Okay, something is failing. So anyways, in order to not miss some time here, this is the synthetic data generator. If you have any question later, just ask us, okay? Thank you, guys.
Thank you very much. Thank you very much, Alberto. Okay, so normally we would have a 5-minute break here, but we are already off time, so I will ask Hania to present use case 4.
Hi, can you hear me and see my screen?
Yes, yes.
Perfect. So I'm Hania. I'm a postdoctoral researcher at Josep Carreras Leukemia Research Institute in Spain. And we are the leaders of the use case 4, which is focused on genomics and electronic health records. Those 2 things are the 2 types of data that we work with and that we want to build models on in a way that is privacy preserving. So without further ado, to explain you how our use case is built, I would like to imagine that imagine that you're a doctor and you have a person that walks into your office and they are worried about getting cancer in the future or any other type of disease for that matter. So you would like to be able to advise them on what they could do based on their risk. So here you can see on this plot a group of different people that might come into the office, and you see that we don't really have a way of differentiating them, right? So we want to find a way to differentiate them based on their risk, to assess their risk. This would give us some variability between them. And then once we first have this, we would like to use this to stratify them into different risk groups. This stratification is something that is commonly done to then be able to use different interventions. So for example, for this very low risk group, you could have reduced intensity screening or no screening, which is first important and not just for the patient, because it can help them if they have less screenings to be less stressed as well. But it's also very important for hospital systems that are often overburdened when it comes to screenings. Then we would have the middle, the average risk group, as we would call it, that would receive the state of the art, which is the typical screening that is usually done. Then we would have the 2 high risk groups, and one of them could, for example, receive a more intensified screening. And the very high risk group could, for example, even go as far as prophylactic treatments if those are available. But how do we do that? One of the ways that this is actually commonly done in many of the countries, if you think, for example, about breast cancer, is the age-based mammograms, where in many countries, after the age of 50 or 55, women start receiving invitations for mammograms every 2 years or 3 years. While this seems like a reasonable thing, if you look at the plot on the right, that in the general population, the prevalence of breast cancer by age of 50 is just 2%. So you think, okay, this is working already at a perfect time. This is quite early. However, this is a bit simplified. Age-based screening is not enough, because now if we look at this group of people that have a specific mutation, a specific variant that gives them a higher risk of breast cancer, by age 50, already 33 to 50% of these people will have breast cancer. So this means that these people would benefit from earlier screenings than that age. So this means there's many other factors that affect the timing of the screenings or the risk of the patient for different cancers. Importantly, these factors often are also different for each cancer types. So what would be the alternative to the age-based screening? Well, risk scores. Those can include different things like age as well, because it is an important factor. But for example, also information about whether the person went already through menopause, or in case of lung cancer, for example, whether they have smoked before, and also genetics. So things like this BRCA mutation variant. What are the different ways that we can improve this kind of screening programs then? This is a note that I like to share. That is an official note published last year by the Health Council of the Netherlands on exactly the opportunities for improvement of the breast cancer screening program that they currently have. That is exactly age-based mammograms. And importantly, here you have highlighted below, they say that they expect that within a few years, this program can be significantly improved through the use of artificial intelligence, also things like machine learning and deep learning, risk stratification, and new imaging techniques. In fact, machine learning is something that is already an active area of research for risk stratification in the cancer context. When it comes to machine learning overall, the machine learning models usually do better the more data they can learn on, especially good quality data. Here on this plot, you can see on the x-axis an increasing amount of the training examples that the model is learning from. Then in the green and red, you can see the two different scores that show the quality of the model, the quality of how well it's learning. And you can see that these scores increase then the more training examples are available. So what does it mean for our use case? It means that hospitals could actually benefit from training risk models together. They would benefit if they could put their data together and train these models. So in this example here, you see, for example, hospitals with some databases of data that they have and that they put together into genetic database and electronic health records database. And it would be very likely that the model that is trained on all of this data put together would be doing better than the models that they would have separately. However, unfortunately, this is not possible to be done in this way because there are different privacy concerns and related legal restrictions that prohibit sharing of this data to protect the patients. So what are the ways that we can circumvent this? So within SECURED, we have been evaluating 3 different technologies for this use case. Importantly, this is still something that is being finished right now, so we don't have the final results. These technologies are federated learning, federated inference, and homomorphic encryption. You have seen them presented already earlier today. I will just touch shortly on them later. Importantly, for our use case, as a doctor, you would need to imagine there are 2 phases in practical terms for you. There is the training phase, which is something that is done just once beforehand, and it includes all the data and model preparation and training. And then there is the inference phase, which is actually something that happens each time a person visits your office and they want to know something about the risk of different cancers. So this is something that will require that the server is going to be connected during specific times, so these predictions can be run. So what does the training phase actually entail? Here we have an example, again, of 4 different hospitals. So first and foremost, you will need to gather the participating centers. You would need to talk a lot to agree on the data that can be used. For example, whether you have an information, all of your hospitals have information about the age of the patient, whether they went through menopause, and so on. And you will also need to agree on the data format, so how this data is encoded. And then once you decide all of this and agree on all of this, each of you have to separately prepare your database according to exactly those instructions. So what is the data that can be used in cancer risk prediction? In our example, for example, we use for lifestyle the electronic health records, and we extract from them for different cancers different lifestyle information that is useful. It can be age, sex, income, medical history. And then, as I mentioned, we encode this. This is an example that shows this. You can see here that for sex, instead of female and male, we have 1 and 0, when 1 encodes for female and 0 encodes for male. This is exactly a type of data formatting that you all have to agree on beforehand, and you all have to follow the same template. This encoding is also important because it helps the model understand a little bit more what it's working with. On the other hand, you can also use genetic information, which can be different genetic variants that you already know are associated with the cancer type. So here, on the other hand, we have an example where we have the patients in the columns and the different risk variants in the rows. And we will have for each variant an information on whether this patient has no alleles of that variant, so 0, 0, 1 allele of that variant, 0, 1, or both alleles, 1 and 1. This is just one of the ways of representing it. But again, you will have to agree on how you encode this. So once you do this, and once you do all of this processing within your specific hospital, you gather this genetic data database, electronic health records database, and this means you are ready to be training the model. So once again, to walk you through what this means. It means you have to gather your database, and it's going to be a database that is full of data. It needs to be a lot of patients' information. You need to include, when we are showing the example of breast cancer, both the cases as well as the controls. So both the people that had cancer as well as people that didn't have cancer, so that the model can learn the features of both. You have to choose different lifestyle features that you think will be relevant to your specific type of cancer. These are some examples that we have used in our own models, and as many variants as you can gather as well. Once you have this data, again, encoded properly, you can run it through the model. We have some model proposals here within the SECURED. And what you will get outside at the end of this training phase is the trained model and some importance information that tells you what the model is seeing as important to predict a cancer or a control. So for this part, as I mentioned, we use federated learning and federated inference. Federated learning allows us to do a shared training in a somewhat private manner. However, it offers less privacy than federated inference. However, in the federated inference, we actually only share the prediction. So we have first local models trained separately, and the prediction is shared. It offers more privacy, but we do not get the same benefit from the shared training. And the federated learning service is also the part of the InnoHUB. So now, after we finish the training phase, we would like to understand what is the model seeing as important for predicting, in this case, breast cancer. One of the things that we can look at is in our general studied population, what were the distribution of the different risk scores that we obtain. And we can see that here we have a concentration. We have some people with a higher risk and some people with a lower risk. Another thing that we can look at is which features the model is seeing as important for predicting breast cancer. And we can see that for overall importance, the most important feature that the model has seen is age, which we know naturally makes sense because the older we are, the higher the risk of cancer overall. Also, the information on whether the person had menopause or not. And here in orange, we have different risk variants that are either giving more breast cancer risk or less breast cancer risk. Another thing that we can look at in the terms of features is which type of values of features contribute more to the model predicting the specific person to be the case of cancer or the case of control. So here we can look simply at the example of age that is pretty straightforward to understand. We can see that the higher the age, the more likely the model is to say that this is a person that might have breast cancer, which naturally makes sense because, again, the older we get, the higher the risk of having any type of cancer. So this is something that can serve as a validation of the training phase of the model. Then we can move on to the inference phase, which is, as we said, something that will happen anytime a person visits our doctor's office and they want to know something about the different cancer risks that they might have and how they might want to adjust their lifestyle. So with this person's consent, we would need to gather their data and run it through the model to obtain the predictions. So in this case, instead of having a full database full of patients, we have just one individual's information. So it's going to be a single record. We will need to gather the same type of information that we have gathered for the training of the model for this person, so both lifestyle and genomics in this case. We will need to encode it in the exact same way as well. And then using our already trained model from the trained phase, we will input this data there and get the result. So what will the model give us? It will give us a risk score, which is the prediction probability of whether this person is likely to be a cancer case or not. We will also be able to see where within the population of people this risk score is located, so whether it's a high risk compared to the population or low, and also why. So based on which features is the model making these decisions. So to show you first, if you remember this plot of the population risk scores, I will show you two cases, one that has a very low risk compared to the population and one that has a very high risk. So let's focus first on the high case. We can see that here the model assigned a high risk score, and moreover, the reason that it made this decision is because this person was already 84 years old and they have different variants that confer a higher risk of breast cancer. When we compare it to another case, the one from the lower end of the spectrum, we can see that this person was much older, and that's why the model made this decision, as well as they didn't go through menopause yet. I wanted to also make a quick note here that I haven't mentioned the homomorphic encryption before, but I just want to signal to you that whenever you see in any of the plots here this green lock, it's to let you know that all of the data that enters or exits the model is also, on top of everything, encrypted to further the privacy. I also want to note that the SECURED consortium has provided advances to all three of these components in both theoretical and practical terms beyond the state of the art. Before I finish the presentation, I want to give you an important note and limitation here. So to be actually used in this way in the clinic, machine learning-based risk stratification needs to first go through clinical trials. So it needs to be officially evaluated as a method. While this is not yet done, as far as I know, for any cancer risk stratification, there is this pilot trial that is happening already for machine learning-based risk stratification in the emergency department context. And so what we are doing in our use case is we are not trying to develop right now the best machine learning score that will be evaluated in clinical trials. We are rather looking to the future when this is already happening, when this machine learning-based risk scores for cancer are already evaluated and are already present within clinical practice. And we want to further them even and improve them even more by allowing through the use of privacy-preserving techniques, the usage of them by combining the data of the different hospitals together. So the goal of our use case is to assess the feasibility of this balancing of the privacy, accuracy, and the cost for cancer risk prediction in the multi-hospital scenarios. Here are the three of us, our team at the Josep Carreras. We are also working with great technical partners here at the SECURED. And if you have any questions, I will happily take them now.
Thank you very much, Hania. Are there any questions, by the way, for Hania? I don't see any in the chat. In any case, if someone has a question, please write it down in the chat. We move now to Giorgos Tasopoulos, who is going to show us the anonymization decision support service. I said it correctly this time.
Yeah.
Okay, Giorgos, you have the floor.
Let me know. I'm sharing the screen, right? You can see it.
Yes, yes, yes.
All right. So hello from me. I'm Giorgos. I'm a PhD student in the University of Amsterdam, and I will be presenting the anonymization decision support service offered by the InnoHUB. So this service actually aims to support the user that wants to use the the anonymization software that is offered by the InnoHUB, which is also was presented before by Juan, and in the form of multiple decision trees that can be divided in phases. So the user goes through these decision trees and is informed of the actions that can be taken by the anonymization service, let's say. So after some introductory text here, we are presenting with the first decision tree in the phase 1, which is actually the pre-anonymization phase. So the user can click on this and it's presented with the first question. It says, is your data time series data? We can see that if we hover over the question, we have a tooltip with some extra information about the question. We'll click no for now. We're presented with the next question. Does the data involve dates? We'll go ahead and click no again. Does the data involve hierarchies? Again, there's a tooltip explaining how the hierarchical data are. We can click no here again. Now we have the question that do you need to change the structure of the data? And we can click yes, and then the outcome of the tree is that the pre-anonymization tool should be used. In addition to that, we have some screenshots from the actual tool that was also presented before. We have some text explaining what are the actions that can be done. And also I want to note here that if we clicked yes at any of these previous points, we will be presented with the outcome of that the pre-anonymization tool should be used. At this point, we can click here on the reset and continue to the next phase. So now we'll go through the decision tree about the anonymization tools that are offered by DANS 2.0. We are presented with the first question about if we want to use KM anonymity. The tooltip here explains briefly what KM anonymity is, which is actually a weaker form of K anonymity. In this case, we'll click no. The next question is your data set small and embed set values? And we'll click again no here. And the outcome is that we should use legacy DANS on ARCs. It's also called LDANS. And again, we have some screenshots of how the actual tool looks like if you were to use this anonymization tool. And we have again here a screenshot of an original dataset on A, and on B, the anonymized dataset. And finally, we have a screenshot of a report that is produced by the tool that generates detailed statistics about the anonymization process and also includes privacy risk detection. So we see here some risk scores. If we reset this tree just for visualization purposes and we select, for example, yes in the question about KM anonymity, we are prompted the outcome of the tree is to use Amnesia. Amnesia is a different tool for providing anonymization on datasets by DANS 2.0. And again, we have some screenshots here. This is how, this is the different downloadable anonymized datasets from the different hierarchies. And here we have some examples about this is the original dataset, and these are anonymized dataset from different hierarchies. We can click on the reset option, which will go to phase 2. And if we would like, we'll go also back to phase 1 and explore the tree a bit more, or use it for a different case, with different data. That's it for this service. If you have any questions, feel free to ask.
Thank you very much, Yorgo. Are there any questions? If there are, please write them in the chat, and we are going to answer them in the end. And we are going to move on to our last presentation, Duško Milojevic, who is going to present the GDPR, let me see exactly how it is called, the legal GDPR compliance check.
Can you hear me, Gerasimos?
Yes, I can hear you. I am sharing the presentation.
Okay, thank you very much.
I think we can see it now. Give me just a minute to mute my microphone.
I still cannot see it. Okay, thank you very much. Okay, good afternoon to everyone. I'm Duško Milojevic, PhD researcher at KU Leuven, Center for IT and IP Law, which acts as a legal and ethical partner in consortium. So before going through GDPR compliance service, I will just briefly provide some context background. So basically, recent studies in healthcare domain pointing out that Europe is generating more health data than at any point in the history, and yet researchers are still struggling to access and use it, which significantly constrains research and innovation. These studies, which also include Commission studies, consistently show that although health data is one of the most abundant and valuable data sources in the EU, its secondary use for research, for instance, innovation or AI development, remains extremely limited. For example, Commission recently highlighted that some of the persistent barriers that are present are low trust, fragmented governments, and significant legal uncertainty when it comes to reuse of health data. And this hesitation is not surprising. For instance, health data is classified as special category of data under the GDPR, meaning it's subject of the highest level of the protection. Hospitals and other healthcare institutions are understandably very cautious when it comes to sharing health data. Even an unintentional misuse of sensitive data can trigger really severe GDPR fines, potentially reaching even up to 20 million. So this risk alone makes any data holder far more comfortable not sharing data at all, even when the intended use is beneficial or ethically sound. As a result, this kind of creates a climate where organizations prefer rather not to share data at all than to risk non-compliance. On top of this, organization also must navigate increasingly complex and fast-evolving regulatory landscape with the new frameworks such as Data Governance Act, Data Act, AI Act, and health data spaces. Many data holders are unsure about which rules applies, what safeguards are required, and where the boundaries of lawful secondary use lie. This complex regulatory landscape is even difficult to navigate to experienced lawyers, let alone to hospital with limited resources. So on the other hand, many legal norms are drafted at high level, leaving significant room for interpretation. This also leaves some space for flexibility and allows regulatory frameworks to remain technologically neutral and adaptable, but it also creates uncertainty for practitioners who must translate these legal, abstract, or ethical principles into concrete and operational steps. One of clear example is the principle of data minimization under the GDPR. It obliges organization to know they should collect only what's necessary for the purpose, but there is very little or no guidance at all how to practically implement these principles set out by the GDPR. So this combination of high sensitivity, fear of the sanctions, regulatory uncertainty creates environment where large quantities of health data remain locked away in isolated silos, inaccessible to researchers who couldn't use them to drive medical progress or develop new AI tools. So this is precisely where secure technological solutions are so important, and where tools such as synthetic data generation facilitate overcoming these challenges. Core ambition and one of the main objectives, as Francesco said in introductory part of the Secure project, is to develop technological solutions that are not only innovative, but also which are fully aligned with ethical and legal requirements. And to support this project includes several dedicated tasks focused on ensuring legal and ethical compliance, covering issues such as data protection, cybersecurity, and so on. Our goal is basically to embed compliance and trustworthiness from the very beginning, not as an afterthought. So by combining technological innovation with robust ethical and legal foundations, Secure aim to help unlock the full potential of health data for secondary use, while ensuring at the same time individuals' rights to remain protected in trusted environment. Okay. I don't know, you can keep the previous slide, please. So I will just briefly walk you through what legal GDPR compliance check service actually offers and why it matters for anyone working with sensitive data in project. So when working with the health data or any type of sensitive data and information, one of the biggest challenge for researchers and developers is just simply knowing which rules apply. Between GDPR, data governance law, and AI regulation, including here cybersecurity requirements, the legal landscape can become really overwhelming. Our compliance check service is designed to make this process much easier and far more transparent. So, firstly, the system helps user to identify relevant legislation and guidelines for a specific use case. Sorry. So you don't have to search across different EU websites or regulations. The key requirements are already brought together. Second, service builds on the work already done and conducted in the project. So we have dedicated deliverables that map the entire legal and ethical framework, and which serves as a regulatory roadmap. Deliverables in the project break down the essential concepts from the data, from GDPR, data governance rules, AI regulatory requirements, and cybersecurity obligations. These deliverables form the foundation for ensuring that the smart interface and the secure technologies are developed and deployed in legally and ethically compliant way. For user, all this information will be made accessible through the knowledge base, where selected documents and explanations are stored in one place. Additionally, the service also connects end user with practical guidance from EU authorities such as EU Data Protection Supervisor, EU Data Protection Board. These bodies publish opinion, recommendation, and interpretations on the GDPR and related issues that are incredibly useful when you need to understand how law should be applied in real-world scenarios. All of this means that user can rely on compliance check service not only to understand their obligation, but also to how to implement them correctly. You can go to the next slide, Erasmus. So another feature designed to support user is GDPR compliance decision tree, which I will show in a second after the presentation. So this basically this tool helps end user to quickly understand some of the core GDPR concepts and evaluate whether the regulation apply to specific scenario. Instead of let's say reading a long legal definition or navigating a complex document, users are guided by step-by-step a series of simple but intuitive questions, such as whether the data relates to a natural person, whether the person is identified, and whether the use case involves personal data. So each answer dynamically shapes the next question, eventually leading the user to a clear conclusion about whether the GDPR applies. This is particularly helpful for non-lawyers or people who doesn't have a legal background, but who need to check and perform quick initial screening before diving deeper into legal requirements. But yeah, it's important to know that goal of decision tree is not to replace legal advice, but to provide, let's say, practical first layer of support. It helps user to build confidence and understand the basic logic of the GDPR and avoid common misconception. At this stage, we have developed two complementary decision trees designed to support user in navigating GDPR concepts. The first decision tree focuses on the foundational questions of whether the data at stake qualify as a personal data and whether the planned activity constitutes processing with the meaning of the GDPR. This aims to help a user to make an initial qualification and classification and quickly understand whether the GDPR is triggered at all. In practice, these steps already resolve a large portion of uncertainty, especially for teams without strong legal background. So also we are now developing another decision tree that goes one level deeper by examining roles and responsibilities of end user. This tool will guide the end user through the criteria for determining whether they qualify as data controller, data processor, or potentially joint. We speak about joint controllership. This is also essential because many compliance obligations stem not only from the technology itself, but from the role of organization and the role it plays in shaping the purpose and means of processing. Generally speaking, together, the decision tree aims to, let's say, demystify core GDPR concepts and help user to understand not only what rules apply, but also why they apply. When combined with the legal and ethical guidance documents available in the knowledge base, the decision tree becomes a practical entry point for ensuring that any data processing activity is grounded in correct legal framework. They support consistent informed decision making and aim to reduce risk of misinterpretation. So GDPR compliance check is placed in the services. So you can see it here. So decision tree at this moment we have two decisions tree. So for instance, are we speaking about personal data at all? This should guide the end user to check whether the data at stake are at all personal data, so that they can later on check furthermore guidance. As same as previous speaker provided explanation, I won't go and dive deeper. It's like a bit self-explanatory. So outcome of this GDPR applies, and this should direct the end user who use this kind of services to go and dive deeper with guidance provided by EDPB and check for additional responsibilities and obligations that comes from GDPR. So in essence, at the moment there are two services, and we are developing the third one, which will be a bit more complex, how they are going to recognize their role in data protection processing environments. So basically that's all from my side. I'm happy to provide any other clarification if needed, and thank you for your attention.
Thank you very much, Duško.
Thank you, Erasmus.
So we are actually reaching, sorry, my screen was lower. Okay, so we reached the end of our webinar. I hope you see my screen. Okay, so when you will log off this webinar, you're going to receive a survey that you can complete to give us feedback. If you're viewing this at a later time, you can also, I will try to put a link in the description below, so you can also give us feedback about the webinar. The project will end in the end of 2025. So if you want to follow up and see these tools and services in their final form and use them, please visit our websites. The first one is for the project generally. The second one is for the InnoHUB. You can also follow us on social media and be informed about events, new videos that we're going to make, and also you can subscribe to our newsletter. We have one more newsletter to send at the end of the project, where it will contain all publications, all the deliverables, the most important videos that we will have uploaded on YouTube. So keep in touch. Thank you very much.